Thank you for joining us today. We're here to talk a little bit about vetKeys. I'm Aisling Connolly. I'm a researcher here at DFINITY, and I'm joined by my good friend Franz-Stefan, who is also working here at DFINITY on crypto stuff, right?
Yes, I'm an engineer in the cryptography team and have been recently working on the vetKeys technology. Cool.
This is something that we've been working on for a while now. It's still very much work in progress. If you look at anything on the internet, if you look at anything in blockchains, you know that privacy is a pretty important aspect. It comes up in absolutely everything you do, from browsing to authentication to payments and all this sort of stuff that you see as a user. But also if you're a builder, you see that it comes in multiple places, and sometimes the crypto gets tricky, and particularly on blockchains when you try to remove this central point of trust and you have all this stuff flowing around publicly, it gets pretty difficult to manage secrets in public. So vetKeys was our kind of attempt to solve this problem of keeping secrets on blockchains. We try to make it easy for developers to use, so we hope that's actually the case. Today we will give a bit of an overview of some of the kind of fundamentals that maybe you would like to understand, and give a bit of a demo about an API which is still just being proposed, but hopefully will be in production soon. So with that, I guess, do you have anything to say? Or let's go.
Let's start it.
Cool.
On the slide.
Let's go. Okay, then let's dive in and see a bit more what we mean about enabling privacy-preserving applications on the IC. So I guess first it's good to think a bit for a second why we even care about encryption. As I said, anytime you use the internet, anytime you do anything these days, encryption comes into it in some shape or form. And the same happens when you use blockchains. And while they're very good for integrity and availability, they're quite bad for confidentiality. I'm sure you've been in the situation where somebody has seen transactions that you've made, or you've checked your own wallets, and while this is a great thing, in many cases, it's not so good for confidentiality. And if you want to build kind of secure applications or more kind of commercial applications where you need data to be secure and private, whatever, this is not the best situation. So another problem that comes in when you start trying to do cryptography or secure applications or data protection or any sort of privacy stuff is that managing keys is hard. I mean, if you look into this at all, you'll see that you have one key and then immediately you've many keys and then you've any amount of users, and it just gets out of hand very quickly. Managing devices and things across devices and wanting convenience and usability, it's just very difficult. And we have seen this in previous examples of applications built on the IC. And while it's possible, it just makes it difficult. And when you have a kind of security sensitive thing, simplicity is always better, so that you have less chance of making mistakes. In trying to manage keys, sometimes they're stored in the browser, but this is unreliable because it can be deleted when you remove cookies, or it can be exposed via malware, things like this. There's a lack of support from trusted hardware, so if you want to use cryptographic keys for things other than, let's say, authentication, they're not so much supported. And again, cross-device syncing is difficult. Like using your phone for one task and trying to then pick it up later on a laptop while the key is stored maybe on the phone or in the browser where cookies are deleted. You see, it gets out of hand very quickly. And so we really kind of hoped to open a new spectrum of confidentiality requiring business applications on the IC. So anytime you want to do anything with customer data, or anytime you need privacy, or there's a whole host of applications which we've described kind of in detail many times. We will put some links in the comments or in the comment box below, so have a look there if you want to see lots of inspiration. But here we keep it a bit more high level. What is the agenda today? We would like to give a bit of an overview of what threshold key derivation is, because it can get a bit technical. There are some things to understand. We'll give a bit of an overview of the topics that Franz-Stefan will cover in the demo. I'll just give a bit of a kind of quick intuition, high-level walkthrough, and he will then later show you through the code in the demo, and you'll see how to do everything. All of this code is online. You can check it. You can build upon it. We'll also put the links in the comments below. So, just as a bit of a high-level view of vetKeys, we want to enable canisters to deterministically derive strong cryptographic keys. The keys can be used for multiple things: symmetric encryption, asymmetric encryption, and decryption. Signatures, pretty much whatever you want. Derived keys can be delivered to the canister or straight to the user front end. So we'll get into this a bit later, but maybe you can already start thinking about why you might want that to be. There's a hint here, keeping things hidden from nodes. And the main use case of all of this is to enable privacy on the IC. Some questions that come up sometimes is whether or not you can do computation on encrypted data using vetKeys. This is not the case, so that's something else. We also work on this. There are some ongoing works from Victor Schupp, who's also here, who's working with Zama. They do a lot of interesting stuff with fully homomorphic encryption. Whole other topic, super interesting as well. Be sure to check it out. But yeah, you won't see that here. What you will see here is some intuition about key derivation and the things that you can use these keys for. So as I said, cryptography is used all over the internet. You'll see it everywhere. Any payment you do, anytime you use a password, it's very likely that there is a cryptographic key derived from this, used for various encryption needs across the internet and any digital space. And like at a very, very high level, the magic of this is that every string can be a crypto key. So suppose you have a canister or a piece of software and you want to encrypt some information or decrypt some information. Often what you can do is enter a password, and from this a cryptographic key can be derived that is then used to encrypt or decrypt the data in the canister. And so this is a very, very, very basic picture that I will build upon over the next couple of slides. So suppose you have a canister or a piece of software for which you want to derive a key, you can call a derive key method. And you need to derive this key from some master key that has these properties that can bestow like security onto other keys. So you want to call your derived key function with the master key. And with this, you also send a derivation ID. So you want to be able to, this is usually, this can be thought of as a password or something like that. So this is from the master key, then you can retrieve a derived key. This is, as I said, a very simplified version, but this is how it works. If you think here for a minute, you'll see that, okay, this is all fine, but this master key is essentially trusted. So you trust that this master key is going to derive for you a key that you can use and somehow have security. In the blockchain world, we don't really like to arbitrarily trust things. So one thing we might want to do is actually distribute the power of deriving the key, not just to a single master key, but across nodes that hold different shares of the master key. And this is kind of one of the main things that we introduced here. So if we want to take a look at threshold key derivation, the picture looks very similar, except that the master key is not just in a single place now, it is secret shared across subnets, across nodes in a particular subnet on the IC. And so the function call looks pretty similar to before. You will want to derive a key. You will call this function. You will give a master key ID just to say, hey, I want to derive a key from this master key. And you will also give it a derivation ID. And this is the crypto magic string from which you derive any key. So the reason you need a derivation ID is that as I mentioned before, like we want to simplify key management. We want to be able to do things across different devices. We want to do things with different users. We want like all sorts of stuff. We want it to be easy. And this means that we will need to retrieve the same key later. So suppose I want to do some encryption now, and I want to do some decryption later on another device. I'll need to be able to retrieve the kind of corresponding decryption key later on a different device in some other place. And so for that, we need the key derivation to be deterministic. So I need to be able to be sure that I can get the right key at the right time from the right place. And for this, we need some sort of identifier. So I need to say that, hey, it's my key from that time. You need to derive that one for me so that I can actually decrypt or do whatever I wanted. And so this is the very kind of basic view of threshold key derivation. And it's kind of on this basic picture that we build everything. And so one question you might have is like, okay, so now I give you some ID, which you magically turn into a cryptographic key. What can I do with those cryptographic keys? One of the suggestions, or one of the most basic things that you might want to do with any cryptographic key is have a symmetric key. And there you will call your derive key function from your canister to the subnet from which you derive a key as usual. And with that derived key, you can, for example, encrypt some plain text message, retrieve a ciphertext, and with that key, then you can also decrypt the ciphertext with the same derived symmetric key and retrieve a plain text. So this is like one very simple example of symmetric key encryption that you can use your derived key for. No prizes for the people who guess what you might think will come next. And yeah, you can do asymmetric key derivation as well. And in this case, anybody can send a ciphertext to the canister. They can derive the key, call the derive key function from the subnet as usual. The subnet, given its secret shared master key, will derive a key, send it to the canister, and the canister can decrypt. And note here that the derivation ID will be something of the canister. And so in this case, this can be used for things like time lock encryption, identity-based encryption, all sorts of fancy stuff, which we will see later in the demos. But this is just a very high-level view of the kinds of things that you can do with derived keys. So one thing that you might ask here is whether or not this is actually, how secure this is, because you're deriving a cryptographic key and sending it to the canister and allowing the canister to do encryption and decryption. And while this is very convenient, maybe it's not the case that you want the canister to actually see the keys that you're deriving. And also note that in this case, the subnet can see the key that is being derived. And so in a case, again, in blockchains, there's always a question of trust. How much do you trust the nodes in the subnet? How much do you trust the canisters? Who do you want to see what? It would be great if somehow the nodes could derive an encrypted key for you so that you can be sure that nodes will never see the key material that you want. And there you have much more security. How do we do this? We want to do encrypted key derivation. And for this, you can just think about it as a very simple kind of transport problem. How can we get key material from nodes to me without anybody actually seeing it? And the main idea here is that we want the key to be derived by the nodes in an encrypted way so that if the key is ever reconstructed, it's encrypted and will never be seen. And for this, we just need to generate a transport key pair so that we can send a public key to the subnet from which we ask to derive a key and say that, hey, while you're deriving this key, make sure it's encrypted to me under my transport key pair. So as you see in the picture here, I can generate a transport public key, a transport secret key. I send the public key, the transport public key to the canister. I call the derive key method as usual. I send the master key ID of the subnet, the key which is secret shared on the subnet. I also now send my transport public key and the derivation ID. And so the subnet now derives the key and also encrypts under this transport public key. And so what is sent back to the canister is actually now my encrypted key. So in this case, the nodes do not see the derived key and the canister cannot see the derived key. There's a lot brushed under the carpet here, but this is essentially the crypto magic that is happening. And yeah, with the transport public key and the derivation ID, we get a derived key, which is encrypted. On the other side, now we see that the canister has an encrypted key, which they send back to the user. The user then, in order to be able to use this encrypted derived key, needs to decrypt with the transport secret key that was generated a little bit earlier. So given that and the encrypted key, they can decrypt and retrieve the derived key, which they can then do for encryption and decryption as before. And note that in this case, the transport public key and the transport secret key are completely ephemeral. It's just needed for this exact one instance of when they call on the subnet to get a derived key, that it can be delivered back to the user's front end. This will be shown in the demo, but to give a quick walkthrough of the steps involved, you first need to generate your transport public key, your transport secret key. You send the transport key to the canister. You call the derive key method from the subnet, which takes as input the master key ID, the transport public key that you generated, the derivation ID, which is needed to derive the key that you deterministic derived key. The subnet will derive an encrypted key for you, send it to the canister, which then sends it back to your user front end. The encrypted derived key is then decrypted with the transport secret key to retrieve the decrypted derived key, which you can then use to encrypt, let's say, a piece of text or whatever. You get a ciphertext, and then you can do whatever you want with your ciphertexts. Maybe this leads me to a bit of a demo prelude. I can continue the example from before by saying, suppose you want to do encrypted file storage. It's a bit like very similar the flow as before. You want to generate transport public key, transport secret key. You call to the storage canister to retrieve a key for you. The same thing happens as before. You call the derive key method from the subnet, given your identity, which let's say is Alice in this case. The subnet derives the key, sends it to the canister. Canister sends the encrypted key to you. You decrypt with your transport secret key. You get the key out, and you can encrypt a file, which you then send to the storage canister. In the storage canister, your encrypted file sits there until you want to do something with it later. What might you like to do with it later? You might want to actually get that file back and decrypt it. So in that case, the same flow follows again. You generate a new transport key pair. In this case, as I said before, they are ephemeral. So every time you want to retrieve a encrypted derived key, you will need to send a transport key, a transport public key. So in this case now, this is at some point later in time when Alice wants to retrieve her encrypted file from the storage canister. She sends her new transport public key, the file name that she sent before, and some method to retrieve the file. The same thing happens as before. The canister calls on the subnet to derive the encrypted key for Alice under this new transport public key. The subnet delivers the encrypted key to the storage canister, which sends it to Alice's front end, who can then use her transport secret key to decrypt the encrypted derived key to retrieve the key that she used to encrypt the file earlier, and then she can use this key to decrypt the file and see the file in the clear. So this is a very kind of high-level overview of how an encrypted file storage and retrieval might work. This will be shown in the demo by Franz-Stefan in a few minutes. I hope it's clear. So another example is to do identity-based encryption. So in the previous example was a bit more kind of like symmetric end-to-end encryption. The identity-based encryption is a bit more like public key encryption, and it's really just to simplify sending encrypted messages. I don't know if you have ever tried to send an encrypted email to somebody, but it's not so easy. Often you have to go look up their public key, which is in some public registry that you have to trust, and is it the right one? Has it been updated? It would be so much easier if you could just send an encrypted email to someone's email address or whatever, for example. In this case, I mean, what would be nice to see is encrypting to people's principals, things like this. But very high level overview, let's say Alice on the one hand wants to send a message to Bob. She wants to asymmetrically encrypt, so like do a public key encryption of a message to Bob. And she just used Bob's identifier as the public key to encrypt this message. She encrypts it, gets a ciphertext, and sends the ciphertext to a chat canister, for example. The chat canister then, the encrypted message sits in the chat canister waiting for Bob to come and say like, hey, I want to retrieve and decrypt my chat messages. And so the flow is pretty similar to before, but just on the other side now we have the second user's front end. Let's call this Bob's front end. Bob now generates his transport key pair to send to the chat canister and asks to retrieve his messages, sends the transport public key so that when his derived key is produced by the subnet, he can actually decrypt it. The chat canister then calls the derive key method on the subnet, given the master key ID as before, given Bob's transport public key and the derivation ID, derives the key, encrypts it, sends the encrypted key back to the canister, who then sends it to Bob's front end. Bob can then use his transport secret key to decrypt the encrypted derived key to get the key that will work to, like the secret key that will work to decrypt the message sent by Alice and get the message in the plain text. So this is a very kind of high-level overview of how identity-based encryption would work with the vetKeys system. And again, this will be shown by Franz-Stefan in the demo in a minute. So now I think I've given enough overview, I've talked enough, I've said enough, I've shown you enough pictures. I think it's maybe more interesting to pass over to Franz-Stefan now to show you some code, show you how you can actually use these tools, how you can build these things, give a walkthrough of the API, what you need to do, what you need to know. As again, you can find the code online that you can start building on top of. Thanks very much.
Thank you, Aisling, for this nice introduction on vetKeys. And now we continue with the demo part. Before I start, I would like to make a couple of disclaimers. At this point in time, everything that you'll see is based on a system API implementation that is a proposal and the proof of concept implementation. So this shows how things could look like in the future, but at this point, things could still change. So please be aware of that. The resources for the full implementation and the integration into the internet computer are not yet fully committed. I think we are all thinking that this will happen sometime soon, but it's not fully committed yet. Second disclaimer is that the timings that you'll see in the demo are not yet representative on how it's going to be in the actual implementation when it's fully integrated in the internet computer. For example, because there are actually no crossnet calls performed yet. So eventually we expect that the latency will be very similar to the feature that is called threshold ECDSA, but we expect higher throughput because the actual cryptographic protocol underneath is quite a bit more efficient. So the throughput will much likely be higher. And the third disclaimer I want to make is that the current vetKD system API implementation that the demos that I will show use is insecure. So do not use this in production. You can use it for learning about the technology. You can use it for implementing your own demos, building on the demos that you'll see. But please be aware that this is insecure because there is a fixed key baked into the canister, and the actual implementation later, the full integration into the internet computer, is needed to make everything fully secure. So don't use this in production or for sensitive data. Okay, so I'm gonna show 3 demos. The first one is a demo of how end-to-end encryption could look like. So this is basically what Aisling showed on her slides that were titled Encrypted Key Derivation. And I'll start with showing the system API proposal that we are making and the insecure implementation of it. And then I'll show a backend application canister that does end-to-end encryption, or that is the basis for end-to-end encryption, which basically retrieves a vetkey by using the system API and then derives from that a symmetric key directly in the browser, which can be used to encrypt and decrypt data. And it's doing so by calling the system API with the caller ID as the derivation ID. And we also have an example frontend that we'll see, and this is using a vetKeys user library, as we call it, which is basically running in the browser as a WebAssembly code. And this will be the part that derives the symmetric key directly in the browser from the vetkey that we received from the dApps backend, from the internet computer. And for encryption, we will use standard AES encryption. So we'll derive an AES key, and we'll use this AES key with the standard web crypto API that's available in all browsers today. Okay, so let's jump to the system API, which is really the basis for this demo and for everything that we'll see. This API is at the moment part of a pull request on GitHub in the DFINITY interface spec repository. So feel free to look it up. You can also give comments if you want. If we look at the exact changes that the PR proposes, and that's the interesting part here, that's the threshold key derivation API. So for people that are familiar with other internet computer features, such as the threshold ECDSA signature system API, we'll see that the API is somewhat similar in the sense there is in both there is a part to derive a public key or a verification key for both vetKeys and threshold ECDSA, and there is the API that performs the actual action, which for threshold ECDSA is the signing part, and for key derivation is to retrieve a vetkey that is encrypted under transport key, as Aisling explained it. So in particular, we have one API that's called vetKeys public key, which optionally takes a canister ID and the derivation path and the key ID. The key ID is the same, conceptually the same as for the threshold ECDSA feature. Basically, that identifies some master key that is held by a subnet. Most likely, this will just be a single key ID that is available on a subnet. So you can then look up later on when we have fully integrated this in the documentation what this key ID is. In our example application, we have just called this test key 1 or something like that. There's also a curve name, so for the underlying cryptographic curves that are used at the moment, and also we envision this initially to be implemented only for the BLS 12.381 curve. So that's pretty much a constant that you would put in here as argument. And the canister ID is optional, so if you don't specify a canister ID, then the derivation happens for the canister that you're calling, but for certain use cases you might want to derive keys for other canisters, and then you can input the respective value here. And for the actual API that's going to be deriving the keys, that's called vetKey encrypted key. And encrypted because the key that you will get back is encrypted under the transport key. And the transport key under which the key that you want to derive is encrypted under is called encryption public key here. So this is the transport key that was mentioned before. Again, the key ID here is the master key that is used to derive the key. Again, that's pretty much a constant, as there will be only one available, at least initially. And then the relevant part is really the derivation information here. So we have the derivation information in this API consists of two parts: the derivation path and the derivation ID. Depending on which use case you're using this API for, you'll use only the derivation ID or the derivation path, or both in combination. And I've actually prepared a slide to give you a little bit of an intuition of when you use what. So for the standard key derivation use case, the derivation, you would only need the derivation, or in general, you can say the derivation path is only needed for use cases where you want to do BLS signing. So you can use this API for, as Aisling already said, for key derivation or identity-based encryption for BLS signing, also some others, but these are the main ones. And the derivation path is actually only needed, strictly speaking, in the use case of BLS signing. So if you use this API to actually create a BLS 12381 signature. For the other use cases, the derivation path is not really needed. However, we do still recommend to use it for proper cryptographic hygiene. And in particular, for key derivation, the derivation ID is typically used, or it's a unique canister specific identifier for the key that you want to derive. And usually, not in all use cases, but usually this is user specific, the derivation ID. And if it's user specific, then the canister, the app canister, must ensure that only the respective user to which this key should apply to can actually access the derived key. So that the canister has the job of doing access control here. So the canister must ensure that only the user to which this key pertains to is able to get it. So that's the derivation ID for key derivation. The derivation path, as I said, in that scenario is optional, but we recommend to use it still for domain separation. We'll see in the demo how this is done. For identity-based encryption, the derivation ID is usually the target identity for which you want to encrypt something. And again, here, the app canister's job is to ensure that only the target identity can actually get access to the respective decryption key, so that no one else but the user for which the encryption is intended for can decrypt. And the derivation path in this use case is optional, but we recommend to use it still for domain separation. And if the API, so the exact API that we've just seen, is used for creating BLS signatures, then the derivation ID is actually the message that you want to sign. And the derivation path is when signing to sign with respect to distinct public keys, so that you can distinguish under which public key a particular signature can be verified. And again, similar to the other two scenarios, in this case, the derivation path is usually user-specific, where the canister makes sure that only the respective user can request signatures for this particular derivation path, so that no one else but this user can create signatures in that name. Okay, so that was a little explanation of how this whole derivation information is used. I have made this very explicit now because the people who have used this API already were always wondering how to use this derivation information correctly, and I hope the table that I've shown has clarified this sufficiently. Okay, so with this API as basis, we can now build an example dApp on it. And the one that I'm going to show is available in the examples repository. Here under, so we have a Rust version of it and the Motoko version. The one I'm going to show is the Rust version, but the Motoko version is very, very similar. So this is under Rust vetKD, under the Rust vetKD folder. And I have another IDE that has this folder as a base folder. So we have vetKD source folder, which contains the backend, the frontend, and the system API. And again, the system API here, we have this insecure implementation of the system API that we propose. And if we look at the candid file that is underlying this, that's exactly the API that you have seen, exactly the API that is proposed in the GitHub PR with the vetKD public key and vetKD encrypted key functions. And we don't need to look in much detail here, but basically the canister implements these two functions, runs some cryptographic protocol that does the key derivation, which later hopefully will be fully integrated into the SE, and you won't need this system API, this insecure system API canister here, because you can just call the management canister directly, which will offer this API then. So the basic demo, if we look at the backend, or in the basic demo, what we'll do is, as I said, derive a key and then derive a symmetric key from that key and use it in the browser directly to encrypt and decrypt some ciphertext. So what do we need on the backend for this? We need two methods, namely one that gives you the symmetric key verification key, which is needed then in the front end for verifying that the derived key you received is actually derived in the correct way. So that's this method here. Very simple. It creates a request that where canister ID is set to none. The derivation path for proper cryptographic hygiene is just set to, it has one element and is set to the text symmetric key. And for key ID, we use basically the only key ID that is master key ID that is supported by the system API canister, which uses the curve BLS 12381 and has the name test key. So that's going to be used throughout all the demos. And then it just forwards this request. So it makes a call to our canister that we've seen before and returns the public key of the response in hex encoded form. And then the method to actually get to the vet key. So we have a method called encrypted symmetric key for caller. So it's, as the name suggests, it's caller specific. So what we do is we create the request where for the derivation ID, we use the caller's identity, which means that only the caller can get to his own key and nobody else can get anybody else's key. And for the public key derivation path, for proper cryptographic hygiene, we use the same domain separator that we used before in the public key method, in this verification key method, which is called symmetric key. And key ID is the one that we've seen. And as the encryption public key, we use what the caller provided us. So when the caller calls this API, he provides us the transport public key. And we just use that in our request to the system API canister to basically make the protocol create a derive key such that it's encrypted under this key. And then we just return the encrypted key that is contained in the response and hex encode it. So now let's look at how this looks when it's running. So here we have the front end. The login part is not super relevant for this demo in a first step. So let's disregard it for a second. Let's look at the middle part here. So encryption with symmetric AES-GCM256 key. So we have a button and plaintext ciphertext inputs. So when I click this button, fetch symmetric key from local usage, we will fetch the vetkey in the browser, derive the symmetric key, and then we have it available in the browser memory. I press the button, now we have this available. So now we can use the key that is in the memory to encrypt and decrypt something. And this is going to be super fast because it all happens in the browser. So if we take some plain text, like, I don't know, quick brown fox, and encrypt this with the symmetric key that we derived from the vetkey, this is, the ciphertext shows up instantaneously, and if we want to decrypt it, we get the plain text also back immediately. If we were now to use this ciphertext under another user, so at the moment I didn't log in, so we use the anonymous principle, but we could do this in a separate browser tab. Could take this ciphertext and log in. Now we're logged in under some identity, which happens to have the principal S7NJNL in this application. So now, if as this user, we would fetch our vetkey, derive the symmetric key in the browser, and try to decrypt this ciphertext, that obviously fails. So let's briefly look into how exactly this front end looks code-wise. So in our front end, we have the JavaScript code that underlies this, and we have three relevant methods here. We have get AES-256 GCM key, which is the code that's executed when I click this button. And then we have AES-GCM encrypt and AES-GCM decrypt, which are called when we call the respective buttons here. So let's briefly look at what happens when we press the button fetch symmetric key for local usage. So first, we need a transport key pair. To create a transport key pair, we need some randomness. How do we do that? We call the standard web crypto API, window crypto, to give us 256 bits, 32 bytes. It gives us a seed, and when we create a transport secret key based on that seed. for doing so, we use a library which we call IC vetKeys utils, which is publicly available. This is what I said before is the WASM code that runs in the browser. So this is a node module that we are importing. And this node module offers various functionalities, in particular working with creating transport key pairs and then performing operations on the transport key pair, such as, and I can briefly show the code here. So this is the source code of this IC vetKeys utils, which lives on GitHub in the IC repository under the folder packages IC vetKeys utils. And the most relevant structures for this first demo are, it's basically just the transport secret key. And the transport secret key has the from seed method. It has a public key method to, once you have a secret key, give you the respective public key. And then what we're going to use is decrypted hash, which is basically the function to derive a symmetric key based on some input. And we'll look at how this is done. Namely, yeah, we create the transport secret key, and then we call the encrypted symmetric key for caller method on the backend of the backend canister, and input the transport secret key's public part. What we'll get back is the vet key encrypted under our public key. So that's one thing that we do. And the second thing that we do is we call also the other method, the symmetric key verification key method. And the only reason that we need this here is because during decryption of the vet key, we also want to verify that the key was derived in the correct way, so that the subnet derived the key according to exactly the cryptographic protocol that it's supposed to do. So, and this verification process needs the public key as well. If you could decide theoretically to skip this verification part, if you would do this, we don't offer API for this, but if one would modify the code that we have to skip the verification, and there might be legitimate use cases for this, then the public part wouldn't be needed. But we do this, or our implementation does this, so we need both the encrypted key and the public key, and then the decrypted hash method, which is the part that in the browser here locally derives from the vet key, the symmetric key, takes the encrypted key bytes, then the public key bytes, and as I said, this is only used for verification purposes. And then it also takes the derivation ID. And again, that's also only needed to verify that the key was correctly created for a particular derivation ID. And in our case here, because the derivation ID is user specific, we use the app backend principles binary representation that we have because we logged in, or if we didn't log in, it's the anonymous users principle, so that we input here. And then we can say, okay, how long should the symmetric key that we are deriving be? In our case, because we're going to use this key for AES GCM 256 encryption decryption. That's 32 bytes. And the final parameter that we have here is symmetric key associated data, which is used again for domain separation. So when we derive the symmetric key here in the browser, we want to say, okay, this key is intended for being used for AES 256 GCM encryption decryption. So we use this as a domain separator for proper cryptographic hygiene. Okay, so once again, we press this button. This is what happens, and then we have this key locally available in the browser. And then when we want to use it to encrypt or decrypt things, or in that case to encrypt things, then we just use the standard WebCrypt API. So very quickly we derive an initialization vector, which needs to be unique per message. So it's just some random value, then we import with the WebCrypt API the raw key, which is basically the output of this function here. We import this so that we have it available as a WebCrypt API object. Then we encode the message that we want to encrypt and call the WebCrypt API. And that gives us the ciphertext. And then we just bundle the initialization vector and the ciphertext together, because for decryption we need both, and hex encode this package and return it. And to decrypt, very similar to before. So first we just unbundle this package of initialization vector and ciphertext into their respective parts, create a WebCrypt API object from the raw key which we fetched before, we decrypt, and we're done. So that's really all that's needed. And yeah, the IC vetkd utils is really a very important part here to make everything run just in the browser. Okay, so this was the first demo. The second demo will be about identity-based encryption. This is also based on the same insecure implementation of the system API that we proposed, and it also uses the same backend canister, but this time we have separate functions just for the IB functionality, and it again uses the vetkd user library. So there wasn't running in the browser to decrypt an IB ciphertext from a vetkey. So how does this look like? In the backend, we have two respective methods. One is called IB encryption key, and one is called IB decryption key for caller. The encryption key is basically just the canister specific vet public key, with the twist that we use again domain separation for proper cryptographic hygiene, where as a domain separator as derivation path, we use the domain separator identity-based encryption. Very similar, we just call the vetkd public key method with this request here that has the standard key ID and the derivation path. And for the decryption key, again, very similar. We have the encryption public key, so the transport public key as parameter, and as derivation ID, we use the caller's identity to make sure that only the caller can get to his own decryption key. Then we call the system API and hex encode the response. So very similar to before. The difference really is in the front end here. And there are two relevant methods in the front end JavaScript, which are IB encrypt and IB decrypt. Okay, so how does this look in the front end? So let's say we want to encrypt some text for a particular user of this canister. How do we do this? So first thing is to figure out what's the principal of the user for which we want to encrypt something. I have this demo open in 2 tabs, so let's log in the second tab as the user with internet identity 10,001. And in the first tab, I log in as user with identity 10,000. And as you can see, the principals that are shown here, so this shows the principal of the user that is logged in. The principals are different. So let's assume we want to encrypt something for the principal starting with BCLD2. So what we do is, in our demo, we paste the principal here in this field. We have some plain text that is, for example, only for BCLD2, and then we IB encrypt this. So what's happening is that the encryption key is fetched from the backend, and then the ciphertext is displayed. And now if we go to the tab where this user is logged in and paste the ciphertext in here, we should be able to decrypt it. So first the decryption key, encryption key for verification is used to decrypt. It's called fetched, and the decryption key is fetched, and then in the browser everything's decrypted, and we can see the text only for BCLD2 is correctly displayed. So now if we would take this ciphertext and try to decrypt it here under the other user, so the one that created it, that actually shouldn't be possible. And as you can see, the decryption actually fails, as expected. And if we look at the code that underlies this, so the IB decrypt and encrypt function. So the encrypt function first fetches the app-specific IB encryption key via the backend method that we've seen before. So it just calls the app backend actor IB encryption key method. Then it prepares the encryption, basically just encoding the message in UTF-8, creating a seed, a random seed that is also needed as part of the encryption, and it saves the principal under which we want to encrypt. So it fetches this from the input box in the browser, and then calls a method in our IC vetKey utils. Again, this is the WASM code running in the browser. So there is a vetKey IB ciphertext struct that has an encrypt function where you put in the respective public key of the canister under which this should be decryptable. Then the second parameter is the principal of the user for which you want to encrypt, then the message and the seed, and then you receive the ciphertext. And decryption is, again, using the IC vetKey utils. So if we jump a bit ahead, so what we basically want to do is we want to deserialize then the ciphertext that we get into a IB ciphertext object, and then this object will have a decrypt function which takes a vetkey as input, which acts as decryption key for the IB decryption. And to get to this decryption key, the process is very similar to what we've seen before. Basically, we fetch, so we create a transport secret key. We fetch, by using the respective public key, the caller-specific decryption key, which only the caller can get, nobody else. And then we also need the public part, the canister-specific public part, because this is all input to the to a decrypt function on the transport secret key that gives us the raw vetkey. Yeah, so with this we've seen all the parts that are involved for the identity-based encryption demo. And to finish, I want to show a third demo, which is somewhat a bit more comprehensive. So this was really showing just the basics that you need. So this is the code, and the demo just show the very basics and have the code for the very basics that you need for the various functions for IB encryption or for symmetric key usage. The third demo is going to be about the encrypted nodes tab that we already have as an example application. So this demo does encrypted node storage. And in particular, this example application that already exists is an app for authoring and storing confidential nodes on the internet computer. And the nodes are encrypted with principal-specific locally generated, so locally in the browser, AES keys. And these AES keys are synchronized across devices, and you can think of devices as different browsers, for example, like different actual physical devices, but also just different browser windows, using some device-specific RSA keys. And this is actually the part that you want to improve upon with vetKeys, because managing these device-specific RSA keys in the backend canister is a bit cumbersome. This can be done as shown in the implementation of the encrypted nodes tab, but when using vetkey technology, this part actually becomes much simpler, because the entire device management part becomes obsolete. And this is what we've done. So we've created a variant of the encrypted nodes tab that underneath uses vetkd and therefore doesn't need all the device management part. And I just want to show how this tab looks like, so you can get a bit of an idea of how powerful this whole vetkd technology is really. So I have the encrypted nodes tab running here. I can log in, and when I'm going to use some test internet identity 10,000, and when I do this, as the app is starting up, as it initializes, it will actually fetch a vetkey, derive a symmetric key from it for the user that's logged in, and then it's ready to go. So if I add a note here and say note encrypted with vetkd, I can store this and maybe create a second one. And these nodes now in the browser are with the exact technology that I've seen before in the basic demo. The symmetric key is used to encrypt the node and then store it in the backend canister. And it can be retrieved whenever you are logged in with that particular user at any device. And we can actually do this if we go to another browser and log in with the same internet identity anchor. We'll see that these nodes are available. And now what's important is that if we would log in with another user, we shouldn't be able to see the nodes. And if we do this with the internet identity 10,001, again, the vetkey is used, symmetric key is derived, but because this is a different user, we don't see any nodes here. And yeah, this basically concludes the third demo that I wanted to show. And as Aisling said, all of this is publicly available. The system API proposal that we have is on GitHub in a PR in the interface spec repository. All the demos are on GitHub in the DFINITY repository under DFINITY repository examples. And again, the base demo that comprises both symmetric key, encryption, decryption, and IBE is available for Rust and Motoko. And we also have the encrypted nodes tab that uses vetKeys in the Motoko folder, but there is also a Rust variant of it. You can use, when you build the app, environment variables to decide if the Rust-based version or the Motoko-based version should be built. And the vetKeys user library is available, as I said before, in the IC repository in the packages folder under IC vetKeys utils. And there's also developer documentation, which we are extending as we go. So the table that I've shown regarding the usage of derivation at the end derivation path for the various use cases probably will also be there. But otherwise, yeah, just look up the documentation and feel free to give us feedback on anything, on the proposed system API, on the demos, and on the technology itself. So yeah, looking forward to your feedback. Thanks.